resistant metal on Earth. Tungsten has the highest melting point of all metals, over 3,422 degrees Celsius. Not even volcanic lava can melt it. Extracted from the depths with explosives. To obtain tungsten, entire mountains must be blasted. Open pit or underground mining is used with dynamite and heavy machinery. From rock to shiny powder. After extraction, rocks containing wolframite or scheelite, tungsten minerals, are crushed and chemically treated to separate the metal. It becomes a gray paste before being solid. Tungsten oxide is mixed with hot hydrogen to create pure metal in powder form. Then, it's sintered and compacted. Used in tools that cut even steel. A saw that doesn't wear out? It has tungsten. It's used to make drill bits, blades, drills, and industrial spearheads. Present in World War II, tungsten was so strategic that several countries fought to control its mines. It's a war metal. The rod from God, or Thor's spear. Some theorists call it that, a tungsten rod launched from space that, due to its speed and density, could destroy cities, without explosives, just with kinetic force. Resists the heat of the sun. Tungsten is used in light bulb filaments because it can withstand being incandescent without melting. It's in your phone and computer. It's found in electronic components due to its conductivity and thermal resistance. You use it without knowing it every day. It's so dense it sinks like a stone in mercury. Its density is similar to gold. If you throw a block of tungsten in mercury, it goes to the bottom like a brick. As you can see, tungsten is present in many aspects of our lives and continues to be key to the advancement of various industries. Would you like to know more about how this incredible metal is extracted and processed? Don't forget to like, subscribe, and share this video so you can keep learning about the most amazing metals. Stay with us. Step 1. Exploration and location of deposits. The first step in tungsten extraction is the exploration and location of deposits. This phase is essential to determine the quantity and quality of the mineral present in the earth. To do this, geologists use various prospecting techniques, including the analysis of soil and rock samples in geologically favorable areas. The main sources of tungsten are two minerals, Wolframite and Scheelite, which are found in igneous rock deposits and hydrothermal veins. Experts conduct seismic and geophysical studies to detect possible underground deposits and obtain precise information about the location of the deposits. Drilling is also carried out to extract subsoil samples and analyze their tungsten content. This information allows mining companies to decide whether mining is viable and profitable in that area. Once a promising deposit has been located, a detailed analysis of its size, depth, and mineral content is performed. This is key for mine design and extraction process planning. Exploration is fundamental because without proper location, the mining process would not be efficient or economical. This step is the foundation for the entire process, ensuring that extraction is viable and sustainable in the long term. Step 2. Extraction of the mineral, Wolframite or Scheelite. Once tungsten deposits have been identified, the next step is the extraction of the mineral. The most common tungsten minerals are Wolframite and Scheelite, and the way they are extracted depends on the location and type of deposit. In vein or lode deposits, extraction can be done through underground or open-pit mining, depending on the depth and extent of the deposit. In open-pit mining, the surface material, called overburden, is removed to access the mineral deposits. This technique is more common when deposits are relatively shallow. In underground mining, tunnels and galleries are excavated to reach the mineral, using specialized equipment to detach the material from the walls and transport it to the surface. Once extracted, the mineral is transported to processing plants. Raw tungsten usually contains impurities and must undergo additional processes to separate tungsten from other elements. During extraction, it's crucial to control environmental impact, as tungsten mining can generate waste that must be properly managed. This step is vital to obtain the Wolframite or Scheelite that will be processed in later stages to produce high-purity tungsten. Step 3. Crushing the mineral. Crushing is a fundamental stage in tungsten ore processing. Once the ore has been extracted and subjected to preliminary selection, it must be reduced to smaller particles to facilitate the separation and concentration of valuable components. In this phase, large ore blocks pass through different types of crushers that operate sequentially. First, a primary jaw crusher is used that reduces blocks of several meters to fragments of 10 to 15 centimeters. These fragments then pass to a secondary crusher, generally of the conical type, which reduces them to sizes of 3 to 5 centimeters. The last stage employs a tertiary crusher or mill, which pulverizes the material to obtain particles of 0.1 to 0.5 millimeters. This size is crucial for subsequent gravitational separation or flotation. Particles that don't reach the desired size return to the circuit to continue their reduction. Crushing must be carefully controlled, as excessive pulverization could generate particles that are too fine and would hinder tungsten recovery, while insufficient crushing would result in particles where the valuable mineral remains trapped in the gangue. The process consumes considerable energy and requires constant equipment maintenance due to the characteristic hardness of tungsten minerals. Step 4. Mineral concentration. After crushing, the pulverized mineral enters the crucial concentration stage. This process seeks to separate the valuable tungsten minerals, mainly Wolframite and Scheelite, from the mineral gangue, significantly increasing the WO3 content. Concentration begins with gravimetric methods, taking advantage of the high density of tungsten minerals, 7.1 to 7.5 g/cm superscript 3. Equipment such as shaking tables, spiral concentrators, and jigs are used to separate minerals according to their specific weight during their movement in water. Magnetic separation is also effective for Wolframite, which has paramagnetic properties. Medium-intensity magnetic fields capture Wolframite particles while other minerals pass by. For Scheelite, electrostatic separation and ultraviolet fluorescence allow this mineral to be identified and separated, as it shines with bluish fluorescence under UV light. The concentration process raises the WO3 content from approximately 0.3 to 2% in the raw or to 65 to 75% in the final concentrate. This material, known as tungsten concentrate, is what is commercialized or subsequently processed to obtain intermediate products such as APT, ammonium paratungstate, or ferrotungsten. Step 5. Reduction of tungsten to metallic tungsten. The transformation of tungsten concentrate into pure metal represents one of the most challenging processes in extractive metallurgy due to tungsten's extremely high melting point, 3,422 degrees Celsius. The process begins with the conversion of the concentrate, WO3, into ammonium paratungstate, APT, through chemical treatment with ammonia. The APT is then calcined at temperatures of 600 to 800 degrees Celsius to produce high-purity tungsten oxide, WO3. The reduction of the oxide to metal is carried out through hydrogenation, a staged process in tubular furnaces where hydrogen acts as a reducing agent. The reaction occurs at progressively higher temperatures. Initially, at 500 to 600 degrees Celsius, intermediate oxides are formed. Then, at 700 to 800 degrees Celsius, WO2 is obtained, and finally, at temperatures of 900 to 1100 degrees Celsius, reduction to metallic tungsten in powder form is completed. This tungsten powder has a grayish appearance and crystalline structure. Its high purity, 99.9% plus, is essential for its subsequent applications. The obtained metallic powder undergoes powder metallurgy, where it's compacted by pressing and sintered at temperatures of 2000 to 2500 degrees Celsius in a controlled atmosphere. This treatment consolidates the particles without completely melting them, creating a dense and resistant metal. The complete process requires rigorous control of conditions such as temperature, pressure, hydrogen purity, and reaction times to obtain industrial quality tungsten. Step 6. Refining of metallic tungsten. After reduction, the obtained tungsten requires additional refining to reach the purity necessary for advanced industrial applications. This process eliminates residual impurities and improves the physical and mechanical properties of the metal. Refining begins with a chemical washing of the metallic powder using diluted acidic solutions that eliminate traces of surface oxides and impurities. Subsequently, it undergoes heat treatment in a reducing atmosphere to eliminate volatile impurities. For applications requiring ultra-high purity, the zone melting refining process is employed. In this method, a narrow zone of the metal is melted by induction heating or electron beam while slowly moving along a tungsten bar. Impurities tend to concentrate in the molten zone, moving toward one end of the bar. Another method is chemical vapor deposition, CVD, where volatile tungsten compounds thermally decompose on a hot substrate, forming a high-purity tungsten layer. Electrolytic refining is also used, immersing the tungsten in an electrolytic bath where it acts as an anode. The pure metal is deposited on the cathode while impurities remain in solution. Refined tungsten reaches purities greater than 99.99%, essential for applications in electronics, aerospace, and precision tools. Step 7. Manufacturing final products, cutting tools, filaments, alloys. Once refined, metallic tungsten is transformed into various final products, taking advantage of its exceptional physical and mechanical properties. For the manufacture of cutting tools, tungsten powder is mixed with cobalt as a binder, 6 to 15%, and carbon to form tungsten carbide, WC. This mixture is pressed into molds and sintered at 1400 to 1600 degrees Celsius, creating hard metal or Widia. The resulting tools are characterized by their extreme hardness and wear resistance, being ideal for high-speed machining, mining drill bits, and forming dies. Filaments for lighting and electronics are produced through tungsten wire drawing. The metal is progressively stretched through dies of decreasing diameter until extremely fine wires are obtained, 0.01 to 0.05 millimeters. These filaments can withstand temperatures above 2000 degrees Celsius without melting. For alloys, tungsten is added as ferrotungsten or metallic powder to steels and superalloys. Added in proportions of 2 to 18%, it provides high temperature resistance, hardness, and wear resistance. The resulting alloys are used in aerospace turbines, drilling tools, and military armor. Other specialized products include electrical contacts, TIG welding electrodes, nuclear reactor components, counterweights, and radiation shields. Tungsten coating through thermal spraying provides wear-resistant surfaces on critical industrial components. And thus concludes the extraordinary journey of tungsten, from the depths of the earth to becoming everyday technology. The next time you use a cutting tool or turn on a light bulb, you'll remember this fascinating process. What aspect of tungsten processing did you find most interesting? The high temperatures needed to work with it? Or perhaps its transformation into carbide for tools? Leave us your comment and tell us what other mineral you'd like to learn about in our next episode. Subscribe for more content about the metals that make our modern world possible.